Welcome to this explainer. Today, we're going to dive into a highly resilient, data-driven control strategy for dual three-phase permanent magnet synchronous motors. You know, as senior system engineers in automotive development, we already know these dual configurations are the absolute gold standard for EV propulsion. But today, we're unpacking some research that completely rethinks how we control these powertrains under extreme duress, entirely stripping away the need for those rigid mathematical models we're so used to.
So think about that for a second. What actually happens to your EV drivetrain when a phase suddenly fails at highway speeds? Well, usually, a sudden loss of a phase means massive torque ripple, dangerous current spikes, and potentially a complete loss of propulsion while the system frantically attempts to figure out what just happened. Current model-dependent systems tend to fail precisely here, simply because they rely on outdated parameters to recover. And in automotive applications, those safety margins are just razor thin.
Okay, here's our agenda for today. We'll cover 1. The PMSM control challenge. 2. The adaptive observer solution. 3. Surviving sudden phase failures. 4. Efficiency under load changes. 5. Calculating electromagnetic torques. And finally, 6. The engineering verdict.
Starting off with Section 1, the PMSM control challenge, classic model limitations.
Right, let's talk about classic Model Predictive Current Control, or MPCC. We all know it relies far too heavily on precise parameters that inevitably drift. I mean, think about stator resistance, inductance, and back EMF constants over a 10-year vehicle lifespan. In a lab environment, sure, MPCC works beautifully, but out on the real road, as the motor degrades and thermal cycles really take their toll, those parameters drift, making MPCC a massive liability. The model essentially becomes a ghost of the actual hardware. Now, a model-free approach completely bypasses this vulnerability by utilizing ultra-local input-output data. Instead of relying on some static mathematical model, the controller looks at immediate, real-time input and output data to estimate short-term system behavior. It literally doesn't care what the inductance was yesterday, it only cares about what the motor is doing right this exact millisecond.
Moving on to Section 2, the adaptive observer, dynamically tuning AGESO.
So, the Adaptive Gain Extended State Observer, or AGESO, brilliantly solves the disturbance problem by continuously monitoring error trends and dynamically adjusting its gain to compensate in real time. For the drivetrain experts tuning in, you know the struggle of bypassing the need for an accurate plant model. Well, AGESO cleverly treats the unmodeled dynamics, the parameter mismatches, and the external faults as one lumped extended state. By utilizing a dynamic tuning rule for its gain matrix, it achieves incredibly fast convergence, fighting off measurement noise and transient faults without needing rigid mathematical models holding its hand.
Next up, Section 3, surviving phase failures, open phase resilience.
Let's look at the actual simulation data where a single-phase open fault is introduced right on the alpha axis winding. Because this system is entirely model-free, it doesn't need to panic and recalculate massive parameter tables when that alpha axis drops out. Instead, a fault-aware Clark-Park transformation instantly adapts. And get this, the current imbalance is fully corrected in under 10 milliseconds. The system redefines its control logic dynamically, so the motor just continues to spin smoothly, maintaining torque output and keeping that inverter online when the hardware snaps.
Section 4, efficiency under load, dynamic load handling.
You know, driving isn't just a steady cruise on a flat highway, right? It involves hills, towing loads, and completely varying terrain. In the data, a sudden increase in load torque hits the drive right at the 0.6-second mark. If you hit a drive with a sudden torque load like that, a traditional fixed-gain extended state observer, or FGSO, completely fails to adapt quickly enough, which causes severe tracking overshoots. The current spikes and the speed waveform visibly wobbles. Conversely, the AGESO instantly estimates the new load and maintains perfectly stable waveforms. Its adaptive gain rapidly tightens the tracking loop the exact moment the error trend begins to spike, rejecting that disturbance seamlessly.
All right, Section 5, calculating torques, 6-phase PMSM math.
By splitting the dual three-phase machine into orthogonal alpha-beta and XY subspaces, we gain immense mathematical clarity over the motor's transient behavior. For us as senior system engineers, this is exactly why we care. In a dual three-phase setup, treating it as a single messy system is just a total nightmare.
But by using this transformation, the fundamental components responsible for torque production are cleanly separated from the harmonic components. Those harmonics really just generate losses and vibration, so isolating them translates directly to better vehicle range and vastly improved NVH, noise, vibration, and harshness.
This specific calculation method is what allows the controller to isolate those fault conditions incredibly smoothly, completely eliminating the reliance on slow, memory-intensive traditional switching tables. Because we mathematically isolate the XY harmonic subspace, the controller can actively monitor and suppress those harmonics without interfering with the primary alpha data torque-producing subspace. This allows the system to suppress torque ripple to under 3% during an open phase failure. Think about that. Keeping torque ripple under 3% during a critical phase failure is a massive achievement in automotive EV drives.
And finally, Section 6, the engineering verdict, data-driven performance.
Let's actually look at the hard data and the sheer delta in performance across the board. Standard MPCC has a total harmonic distortion of 4.8%, takes 30 milliseconds to recover from a fault, and suffers a pretty nasty 7.2% torque ripple. But when we pair model-free control with our adaptive AGESO, it cuts harmonic distortion down to an incredibly clean 1.9%. It slashes fault recovery time to a third of what classic MPCC can achieve, just 10 milliseconds. And that torque ripple? It drops all the way down to 2.8%. Honestly, it is a night and day difference.
And because it completely avoids heavy matrix inversions and lookup tables, the computational overhead is a mere 120 microseconds per control loop on a standard digital signal processor like the TI C2000. That makes it perfectly viable for real-time automotive embedded systems. Basically, you get world-class fault tolerance and precision without needing a literal supercomputer strapped to your inverter.
So the crucial point to take away from this explainer is this. If we can mathematically eliminate model dependency and recover from hardware faults in 10 milliseconds, which is a time frame so incredibly short the driver literally wouldn't even feel a loss of propulsion, how will you use this to redefine the reliability of your next powertrain? The transition from rigid model-based control to an adaptive, data-driven architecture is no longer just theory. The data proves it's the future of resilient drivetrain engineering. Thanks for diving into the drivetrain data with me today, and I'll catch you on the next explainer.